In this video, I discuss aspects of algorithmic problem solving as found in Chapter 3. Algorithmic problem solving is not found only in Chapter 3, but it's very prominent there. It's a skill that really is found throughout general chemistry, and it's one that we really need our students to be able to master. When we look at the different topics in the different sections within Chapter 3 involving reactions and stoichiometry, many of these include algorithmic problem solving. Looking at a progression of the ideas as we move through the chapter, and also then the topics as they're found based on their degree of difficulty, and with the thicker lines representing ones that are skills that we need to take away from Chapter 3 and use elsewhere in the chapter, elsewhere within the semester. We find that many of the topics that are more difficult for students can be connected to algorithmic problem solving. Some of these could be conceptual as well, but oftentimes are algorithmic. Now, I've used the word algorithmic and conceptual. Science education research has focused on this for a couple decades now. And research has shown in many disciplines, not just chemistry, that students can answer questions by applying algorithms without also having conceptual understanding of the topic. On our exams, we include both algorithmic and conceptual problems, and we really want students to become proficient with both types. What do I mean by algorithmic problems? Rules, flow charts, instructions, all of those are things that come to mind when I'm thinking about algorithmic problem solving. If you can write a flow chart, if you could write a computer program for how to solve a particular problem, in a way, by definition, that's algorithmic. That can be contrasted with conceptual problems where that would not be possible. Examples of algorithms that we find within Chapter 3. Here are progressions that a plan is being given that the student can follow. If you have a plan that can be given to follow, then it's algorithmic. Empirical analysis would be an example. Combustion analysis is an example. In terms of stoichiometry, there's a description both for using a dimensional analysis or using a BCA table with a limiting reactant. In all of these, there's an algorithm that can be followed. What leads to successful algorithmic problem solving? Well, it begins by problem conceptualization and classification, followed by having a strategy, being able to execute that strategy, and then finally the self-efficacy of the problem solver, a belief that they can solve the problem and persist as they move through it. If we think about these, the first one, problem conceptualization and classification, experts are great at problem conceptualization. By simply reading even part of a question, oftentimes an expert can say, oh yeah, I know exactly what I need to do in this scenario. How about this? Could you classify this question? What type of question is this? Just based on the information that's being presented in abbreviated form here, even with things being covered up, I would identify that as a Hess's Law question. Just based on the format, this could have been written in Greek. If it's set up with, this was the setup where there were multiple equations with the data given, I can right away recognize that as an expert who has seen these types of questions again and again as one involving Hess's Law. Now, I mentioned this term problem solving. Some of the field here of chemical education, science education research would say, let's be careful with how we use that phrase. What really is a problem? And how is a problem different than an exercise? With a problem, there's a gap between what you know how to do and what you're trying to accomplish. An exercise, in contrast, synonyms that appear: practice, apply, implement, utilize, train, drill. All of those are ones where you're not trying to generate a new plan for something that's novel. You already know how to do it, and you're being asked to practice, apply, train, drill, and utilize it. If we look within the general chemistry textbook, it's intentional of calling the end of chapter questions there exercises, complete the exercises. They're all grouped together, and the learner is asked to develop that particular skill and apply it again and again. I would argue that an expert has turned a problem into an exercise. It's no longer novel. They can conceptualize it and right away recall the appropriate strategy. Questions like this provide useful exercise. And by that I mean when they're listed at the end of the chapter in a whole series of similar questions, but not with the problem classification stage. It gives a heading right here that these are going to involve empirical formulas from analysis. It gives a section where you can find more information. And there's just one after another on this. So this is something that could be providing an exercise in the problem solving, but it's not involving any aspect of the classification. To give you an analogy, batting practice, in that case, you know what pitch is coming. Here's a fastball, another fastball, another fastball. In the actual game, it's not like that. Batting practice is not the same as the game. In the game, the goal of the pitcher would be, no, I'm going to confuse the batter. I'm going to change things up. This is pointing out how being able to recognize the task in hand is a really important first step that if you're simply doing exercises, it won't be included. So an implication of this for both teachers and students, don't underestimate the importance of the first step. It is something that's going to require practice as well. One suggestion, student-generated flashcards that can be randomized. This is a useful way to practice the conceptualization. Write different representative questions on flashcards. What's nice about that is then you can shuffle it up, you can randomize it. Now, if we're seeking to improve this step right here of problem conceptualization and do better with that particular first step, another important detail to consider is in the question itself, are there particular characteristics of or details that it's especially important to be alert to? To ask you something not chemistry related, consider this question right here. Is one red line longer or shorter than the others? And are you sure of your answer? I would argue that if you're sure of your answer, if you're going to say they're all the same length, I bet you've seen this question before. Because when you look at this, your very first impulse would be to say, no, I think that that middle one right there looks like it's longer than the others. But you've been able to override that first impulse because you've seen this question before and you knew an important detail to look out for and how to analyze a question was taking you in a different direction. Okay, your very first impulse was flawed, but you've learned how to override that. And I think you've learned how to override it by seeing this particular question before. That idea of what is our initial impulse and what's the plan that we are then going to have, this is relevant for chemistry problems too. When I look at these two questions right here, I would quickly classify them as an expert as combustion analysis. I see the word combustion and I see information given for the amount of CO2 and H2O that's formed. But the next detail that I'm going to be looking for is it a scenario in which there's only carbon and hydrogen present, or carbon, hydrogen, and something else like oxygen? That's the detail that I'm being alert to because I have a somewhat different plan depending on what the approach is. How about this example? This is involving stoichiometry from chapter 3. Both of these are stoichiometry problems. Key thing that I'm initially looking for, okay, do I have a limiting reactant or not? So in both of these cases, I see a chemical equation. I see information given in terms of the amount, be it moles or grams. But in the second case, okay, I have a somewhat different strategy when I classify this because it's involving a limiting reactant. Now, if we were to consider student success on both of these, you might initially say, well, if there is a limiting reactant that's a more advanced problem, it would be more difficult for students. Another important detail that makes both of these questions comparable in terms of difficulty, and the first one perhaps even more difficult, is this feature right here. In the balanced chemical equation, are the mole amounts equal? Are the coefficients equal to each other? If they are not equal with each other, it makes the question much, much more difficult. When we're looking at questions within chapter 3 involving stoichiometry, the top suggestion I have for instructors and for students is really to make ourselves aware of the details and the information that is provided in the balanced chemical equation, and especially the coefficients. Next step in terms of the problem strategy, For an algorithmic problem, the strategy is just recalled from memory. There's really nothing to figure out. You classified the question, and then you recall the appropriate strategy that you're going to then implement. And you want to be able to recall a strategy that's always going to work. This second part here on strategy, it's important simply to ask about this. If you have different questions, which of these questions have the same first step? Ask about the strategy. You don't necessarily have to work it all the way through to see if the student is classifying the question correctly and recalling the strategy. Given different questions, well, would you use the same approach if this component changed? Again, it's really thinking about, is the strategy that the student is recalling applicable for that particular problem? If factors change, would it still be applicable or not? Simply asking about the problem strategy without going through and executing it, there's a lot of value in that as well. When it comes to the execution, authentic testing is crucial. You can't simply look at a worked example, nod your head, and say, yep, that's what I would have done. Being able to execute it and take it all the way through from start to finish, that's a very important skill, and it's a process that we would want to overlearn. Overlearn is a phrase from cognitive science. Overlearning is once the learner is able to complete the task, they would continue to practice and become more proficient with it. The way they study this would be to say, okay, this particular learner, they can accomplish this task 90% of the time. Okay, if they continue on and continue to practice it, that would then be overlearning. They're already capable at answering the particular question, completing the task, and yet they continue to work at it. This right here, when it comes to an algorithmic problem, is really important. Okay, as one gains in proficiency, it can increase your time. It can help with the time by decreasing the amount of time that it takes. It can increase your accuracy as you go through. And it can also increase your confidence because you just feel more capable with answering those types of questions. In terms of feeling confident, that's related to your self-efficacy, your belief that you can solve the problem. This is found to influence performance, even independent of how capable the learner is with these different stages. If there's a belief that they can solve these types of problems, they're more successful at it. I would argue that anyone can be an expert on algorithmic problem solving. The different steps here of identifying the problem, classifying it, recalling the strategy, and then executing it, this is something that anyone can practice, anyone can become better at, anyone can become an expert on algorithmic problem solving. And with that information, I would say we can also then generate the belief and the confidence that we can answer these types of questions. Just to share an example with you, here's a particular question that we'd find in Chapter 3 that could be on an exam. The first step in terms of conceptualization, I see that this is a combustion analysis problem, and I'd be asked to report an empirical formula. So right away, my problem strategy, I'm recalling the correct approach. And I'm also recalling the correct approach that is going to include the detail that I need to be able to figure out the amount of oxygen present as well. In my own work, when I'm working through the strategy, I want to pause and say, what do I need to be alert to here? Okay, the main error that's made within the process is failing to account for the fact that you get 2 hydrogen atoms for every H2O molecule. So I'm giving myself a little reminder right from the start, make sure to do that part correctly. When I then work through my own execution, when I work through problems like this, I highlight to myself the mole amounts that I've calculated along the way, because I'm going to need to use that information at the end of the problem. If I just write it down and I scribble it along the way, I might lose that. So as I work through the problem in my own problem solving and my own execution, I have found that I am more successful if I highlight that information to myself along the way. In this case, I could even use that information to reduce my choices down to just 2 different options. These are the only 2 that have the correct carbon to hydrogen ratio. Final thoughts for you. I've mentioned how there's 2 different algorithms that are provided for solving stoichiometry problems. There's one that is more aligned with dimensional analysis, and then one that's being introduced for a limiting reactant using what's called a before, change, and after table, a BCA table. Both of these could be classified as algorithms. When thinking about which of these is better, or their use within Chapter 3, I'm thinking about what they mean in terms of the execution. If a student is an expert with a dimensional analysis approach, I don't try to change them. I encourage them to continue using that. If someone has a apt algorithm that they can apply, why replace it? So that's my thought if a student is an expert at using dimensional analysis. However, if a student is learning an algorithm, if they're not an expert on dimensional analysis, I encourage them to use the BCA table. My reasoning is it has greater applicability. I think it's better to learn one algorithm instead of two. If one is being presented as a dimensional analysis approach, but a different one is being mentioned for a limiting reactant, and the limiting reactant approach will work for both, I would rather have the students learn one algorithm instead of two. This greater applicability later on within the course in the second semester, the BCA table is used again and again. Second, as I think about the execution, the BCA table, the student is more likely to write down a balanced equation. The balanced equation then frames the rest of the table. That's where they're providing the information. And writing on a balanced equation and attending to the coefficients, that's the crucial step. That is the number one issue that students have. They go on and use the numbers without writing or reflecting on a provided balanced equation. So if a BCA table makes that more of a centerpiece, I really like that included within the problem strategy. The skills that are not shown in the table within a BCA table involve converting between grams and moles to grams. Only mole amounts are used within the table. That particular conversion, that's very easy for students. That's usually a 95 to 100% question on our particular exams. So if that particular skill is much less important than the previous one, which was using the coefficients that are in the balanced equation, I really like the BCA table because that's a strength of this particular approach.